Okay, our next speaker, also from Logic and Philosophy of Science here at UC Irvine, is Clara who's going to tell us about the relationship between Lagrangian and Hamiltonian formalism, which would have been a perfect follow-on to Neil's previous talk.
Start by saying, I said I was going to I told people I was going to talk about this, and in fact, I am going to talk about it. So in particular, I'm going to be talking about, as Jim said, the relationship between the Lagrangian and Hamiltonian formalisms in what's called the irregular case. So sort of in the theme of this conference, what I'm doing in this talk is asking what the kind of math first view will say about this case. And I think this case is particularly interesting because there are still lots of unresolved debates going on here. And I think that using some of the tools that this math first view pushes us to use helps to at least shed light on what is at stake in some of these debates. So in order to understand what's sort of interesting and distinctive about this case, I'll start by just telling you about the contrast to the irregular case, which is just the regular case, which is the one that at least is better understood. So let's start by just taking Lagrangian mechanics to be such that its models are given by first a state space that's just given by the tangent bundle of configuration space. And the equations of motion are given by the Euler-Lagrange equations that make use of this Lagrangian function L. While Hamiltonian mechanics is such that its state space is given by the cotangent bundle of configuration space, and our equations of motion are given by Hamilton's equations using this Hamiltonian function H. Now, importantly, we can define a map from the tangent bundle to the cotangent bundle given by what's called the Lagrangian transformation, which just in a coordinate-dependent form takes you from a point in the tangent bundle, which is just represented by the position and velocities of particles, or so a position and velocity kind of variable, and takes you to a point in cotangent space that's just the same position, but takes you to the corresponding canonical momenta, which is just the derivative of the Lagrangian with respect to the velocities at that point. Now, importantly, this helps to characterize the regular case. The regular case, in fact, we say that it's the Lagrangian that is regular, or more precisely hyperregular, just in case this Legendre transformation is a local diffeomorphism. Now, this case is one that's been discussed a lot in the literature recently. So in particular of note is that Thomas Barrett recently showed that at least on one way of characterizing the categories of Lagrangian and Hamiltonian mechanics, and he's using the kind of models that I described in the previous slide and the symmetries in this hyperregular case, then we can see that these two theories are categorically equivalent. And the crucial reason comes down to the fact that this Legendre transformation just is a local diffeomorphism in this regular case, and so it's invertible. And we can use this Legendre transformation to define the Lagrangian in terms of the Hamiltonian, and vice versa, using its map and its inverse. And this is easiest to see if we, instead in the Lagrangian way of doing things, we define what's called the total energy, which is just defined in terms of the Lagrangian. And this energy function is just such that it is the pullback under the Legendre transformation of the Hamiltonian, and similarly, the Hamiltonian is the pullback under the inverse of this Legendre transformation of the energy function. So this kind of gives a pictorial representation. We can go from the models of Lagrangian mechanics to Hamiltonian and vice versa. What's interesting about the irregular case is just that it is characterized by the fact that this Legendre transformation is not a local diffeomorphism. And so it seems that the kind of equivalence results that Thomas gives won't go through, at least on the kind of same reasoning that Thomas gives about the regular case. And particularly the kind of irregular cases that are most often talked about are the cases where there are local symmetries in the of the Euler-Lagrange equations that are related to dependencies amongst these equations. And in these cases, there seems to be arbitrariness in the solutions to these equations of motion. And it turns out that in these cases, the image of the Legendre transformation is just some sub-manifold of the cotangent bundle, which we call the primary constraint surface, since it's just some surface defined by the satisfaction of constraints on the canonical variables, the variables of Hamiltonian mechanics. So there are sort of two big questions that I'm going to try and tackle in this talk. The first is, what is the correct way of characterizing the Hamiltonian formalism in this irregular case where the image of the Legendre transformation is just some submanifold of cotangent space? And second, what is the relationship between the Hamiltonian and the Lagrangian formalisms in this irregular case? Now, the first question here is one that has been debated a lot in the literature, while the second one is one that hasn't been explored so much, especially it hasn't really been explored so much in the philosophy literature on symmetry and structure. And I think part of the reason for that is just that the answer to the first question is seen as pretty murky. And so what I'm going to do in this talk is I'm going to argue that, in fact, there is a clear answer to the first question, and this will help pave the way for answering the second question. So some of you who might have seen me give a talk on this topic before will have effectively seen most of the first part of this talk, which is just answering this first question. But the second question is one that I've only been thinking about more recently. So the stuff there's going to be new, but it also means that the stuff I'm going to say there is much more tentative, and I'm going to be giving you some conjectures rather than actual proofs of things. But I hope, just as Neil said, that hopefully you'll be able to provide me with some feedback if you have any thoughts on how to kind of tackle the questions here. But I hope to at least convince you that there are some clear, interesting questions to ask that have yet to be settled. So let's start with the first question. What's the correct way of characterizing the Hamiltonian formalism in this irregular case? So the standard way of doing this traces back to Dirac. So the idea is when there are cases where we have local symmetries in the Lagrangian formalism, we use what's called the constrained Hamiltonian formalism, which provides a way of tracing these symmetries to the constraints that arise in the Hamiltonian formalism. So I'm going to start by just describing basically Dirac's way of doing this constrained Hamiltonian formalism. So the way Dirac goes about doing this is he starts with some Lagrangian, which we're just going to write in terms of some position and velocity variables, where I'm going to assume throughout this talk that time acts as some independent variable. We then define the canonical momentum variables as just the derivative of the Lagrangian with respect to these velocities. So remember, that's just what the Legendre transformation does. Now, in the cases that we're interested in, what we find is that there are certain constraints on the relationship between the position and momentum variables that we write as some function of them being weakly equal to zero, which just means that we can say that they're equal to zero on the subspace where these constraints hold. We then define what's called the total Hamiltonian, which is just the usual Hamiltonian in the regular case, plus some arbitrary combination of these primary constraints. So here I'm implicitly having a sum over I and M here. And the idea is that this total Hamiltonian is going to be equal to the usual Hamiltonian just on the subspace where the constraints hold. So then we derive the equations of motion for some function f as just the derivative of that function with respect to time. It's equal to the Poisson bracket of that function with this total Hamiltonian. So it's just like Hamilton's equations where instead of h, we have this total Hamiltonian. We then use the fact for consistency that it ought to be the case that the primary constraints continue to hold over time. That is, it ought to be the case that when we set the primary constraints into the equations of motion, they should also give us something weakly equal to zero. And when we do that, we find in certain cases that there are further constraints on the relationship between the position and momentum variables that we call the secondary constraints. we can in fact repeat this process, putting the secondary constraints into the equations of motion, setting them weakly equal to 0, and we'll find some further set of secondary constraints. And once we have our full set of constraints, we can classify our constraints according to whether their Poisson bracket with a constraint with all the other constraints is 0, is weakly 0, in which case we call that constraint first class. And when this relationship doesn't hold, we call that constraint second class. Now, the second class constraints, in fact, allow one to fix some of the arbitrariness in the total Hamiltonian. But as long as one has some first class constraints around, we're still going to have some arbitrariness in our total Hamiltonian. Now, Dirac uses this framework to argue the following. He starts by saying, well, this is how we should understand a gauge transformation in this formalism. We should understand a gauge transformation as relating any two states that are possible evolutions from some initial state under the dynamics generated by this total Hamiltonian at some fixed infinitesimal interval. And with definition, he shows that arbitrary combinations of the first class constraints generate a gauge transformation. And he thought that this had some important implications. The kind of main one that's going to be important for us is that he thought on the basis of this fact that arbitrary combinations of first class constraints generate a gauge transformation, that one should, instead of considering the total Hamiltonian as the right equivalence class of Hamiltonians, we should rather extend the Hamiltonian to a wider class of a wider equivalence class that includes arbitrary combinations of all of the first class constraints, so including these secondary ones. Now, as I said at the beginning, kind of this view that Dirac presents of this constrained Hamiltonian formalism has become the standard way of thinking about this formalism, but there have been some arguments in the literature that this picture is incorrect for various reasons. So just to give a few of the arguments that people have given, firstly, there have been some alleged counterexamples to the claim that it's the secondary first class constraints that generate gauge transformations in addition to the primary ones. There have also been alleged counterexamples to the claim that each and arbitrary combinations of first class constraints generate a gauge transformation, so a more general claim. And finally, there have been some arguments that just Dirac's proof of what the gauge transformations are is faulty and limited in scope in various ways. In light of some of these arguments, some of these people have put forward what I'm going to call an alternative picture of the constrained Hamiltonian formalism, which starts by saying, well, Dirac wasn't in fact right about what the gauge transformations are. We should understand the gauge transformations to really be a map on entire solutions. We should understand them to relate any two states that are possible evolutions under the dynamics generated by this total Hamiltonian, but at any time t, rather than at some infinitesimal time. With this notion of a gauge transformation, these proponents argue that it's really a specific combination of first-class constraints that generates a gauge transformation. We ought not extend the total Hamiltonian to include this wider class, equivalence class of Hamiltonians, precisely because on this view, there are just as many arbitrary functions of time as there are these primary first-class constraints. So just to use an example of how these two pictures disagree with each other, let's look at the case of electromagnetism. So in electromagnetism, we can write the Lagrangian in terms of, we'll break it down into vector potential A and just a potential V, which we can just recognize the Lagrangian as effectively being a half E squared minus B squared. And what we find when we take the Legendre transformation of this Lagrangian, we find that there's a single primary constraint, which is just the canonical momenta associated with V. And then when we define this total Hamiltonian and consider the primary constraint under the equations of motion, we find in addition that there is a secondary constraint, which is the divergence of the momenta conjugate to A. And we find that both of these constraints are first class. So at least on Dirac's picture, it seems that both of these constraints ought to generate a gauge transformation. But as I said, this alternative picture is going to disagree with this. And in particular, Brian Pitts has been the main proponent of arguing that in electromagnetism, we can see that these Dirac gauge transformations don't generate a gauge transformation precisely because they fail to preserve solutions. And the way that he effectively argues for this is he says, let's consider transforming A and V by an arbitrary combination of first-class constraints, so of both of the constraints. But then what we find is that if the equations of motion hold for the original variables, so I write it here just for A, then in order for the equation of motion to hold for the transform variables, there has to be some fixed relationship on the arbitrariness that we write associated with both of these constraints, which here are just these alpha and beta. So because there has to be this fixed relationship between them, it's not the case that we can just take arbitrary combinations of the first-class constraint. Indeed, if we just consider the case where one of these things is zero and the other one isn't, then we're not going to have a gauge transformation. It has to be a special combination of these two things. So just to highlight what the tension is here, it seems that these two pictures are going to disagree about what models of the constrained Hamiltonian formalism are symmetry related. So while the Dirac picture is going to say that models where these Hamiltonians differ by an arbitrary combination of first-class constraints are equivalent, this alternative picture is going to deny this. So inasmuch as we want to get a clear picture of what the symmetries are, it would be a bad situation if we can't resolve this tension. What I'm going to do is I'm going to argue that we shouldn't lament because, in fact, we can give a clear picture of what the symmetries are here. And in doing so, I'm going to diagnose what's going wrong in this debate. So in particular, what I'm going to argue is that there's a flaw in the reasoning that's being adopted by both of these pictures in the way that I've presented them. But if we see what the correct reasoning is, we can see that Dirac's picture does lead to the right notion of equivalence between models of the constrained Hamiltonian formalism. And in particular, the reasoning that I'm going to put pressure on is the idea that one first determines the gauge transformation using this equivalence class represented by the total Hamiltonian. And then we use the gauge transformation to say whether we should consider this more extensive equivalence class of Hamiltonians. So in particular, the question here is why should we start with the total Hamiltonian in the first place and not this extended Hamiltonian? And indeed, in a recent paper, David Wallace and Oliver Cooley argue that at least in the case of electromagnetism, if one starts with this extended Hamiltonian, then the Dirac gauge transformations just are the correct ones, both for an understanding of gauge transformations on states and for solutions. And the reason is just if we take our total Hamiltonian and now add some arbitrary combination, like some arbitrary function of the canonical variables in time, multiplying the secondary constraint, then what we find is that this arbitrariness carries forward to our equation of motion for A. So now when we consider the transformed variables, that is transforming A and B by some arbitrary combination of the first class constraints, we find that these transformed equations of motion do hold because effectively we have this extra arbitrariness that's carried forward. But I think there's some lingering question here. So what they've shown is just that if we start with the extended Hamiltonian, then we can see that everything works out. But there's still a question of why should we start with the extended Hamiltonian in the first place? Cooley and Wallace do give one reason. They argue very nicely that we can see, in a sense, that there's a sense in which this extended Hamiltonian formalism gives us something that's empirically equivalent to the total Hamiltonian. But what I'm going to do is I'm going to argue that we can go further than this and show that this extended Hamiltonian can be motivated purely on mathematical grounds. And to do this, I'm going to use the geometric way of representing this constrained Hamiltonian formalism, since I think it provides the best neutral framework for thinking about the correct way of thinking about gauge transformations in this view. So in the geometric way of characterizing the Hamiltonian formalism, we think of phase space as just a symplectic manifold. That is, it's just a manifold equipped with a closed non-degenerate two form, which are represented as lowercase omega. And since it's a symplectic manifold, what this means is that given a function f, we can uniquely define a smooth tangent vector field associated with that function through the fact that this symplectic two form acting on this tangent vector field is contracted with that tangent vector field is just equal to the exterior derivative of f. Moreover, these symplectic manifolds naturally give rise to Poisson bracket structure. The Poisson bracket between two functions is just this symplectic two form acting on the associated tangent vector fields. And finally, the equations of motion naturally arise in this formalism just because of the Poisson bracket structure and the fact that we can characterize the Hamiltonian vector field as being parameterized by time. So this is the case without constraints. So now when we add constraints, in particular when we think about the first class constraints, since those are the ones that are going to be interesting to us, what they effectively do is they define some submanifold of constraint surface, some submanifold of the cotangent space, which we're just going to call the constraint surface. Importantly, what happens is when we define the induced two form on this constraint surface, that is just the pullback of the two form on the full space to this constraint surface, we find it's degenerate, and that is it possesses null vectors, and the null vectors it possesses is just the vector field associated with the first class constraints. So we call two form of this kind pre-symplectic, precisely because it has this degeneracy. And we call the integral curves of these null vector fields the gauge orbits. So just to see kind of what this picture looks like, if we have some three-dimensional space that represents the cotangent bundle, then we can think of that if there is one first-class constraint, then this will define a two-dimensional surface in this space, this constraint surface. And on the space, we can define these vector fields associated with the constraint that are just such that they're tangent to the space and the induced two form acting on these, contracted with these vector fields is just equal to 0. So using this kind of geometric framework, I'm going to give kind of a two-pronged attack against this kind of alternative picture of gauge transformations and give what I think is kind of the right picture of what's going on here. So the first kind of attack against this alternative picture is that it gets the equivalence class of Hamiltonians wrong by distinguishing null vectors that at least geometrically seem to be structurally equivalent. And second, this alternative picture is in tension with the fact that there's a natural sense in which the gauge orbits give rise to an equivalence class of states independently from even thinking about the dynamics. So just what that means is that this alternative picture has to reconcile the fact that under their picture, the dynamics can distinguish states along a gauge orbit, even though it seems that the structure of the constraint surface cannot distinguish these states. So just to go through these two arguments briefly, starting with the first one, that the alternative picture gets the equivalence class of Hamiltonians wrong. So if we confine ourselves just to this constraint surface, the surface defined by the satisfaction of these first class constraints, and then we consider a vector field associated with the Hamiltonian, we can just transform it by adding some arbitrary combination of the vector fields associated with the first class constraints. This is analogous to kind of defining this extended Hamiltonian. But what we find is that because these vector fields associated with the first class constraints just are null vectors of our induced two form, what we're going to find is that its action on both the original Hamiltonian vector field and this transformed one is just the same, just equal to the exterior derivative of the Hamiltonian defined on this constraint surface. So what this suggests is that as long as we're on the constraint surface, the evolution generated by a Hamiltonian vector field and that Hamiltonian vector field plus some arbitrary combination of the vector fields associated with the first class constraints is not going to be distinguished. And notice that there's no difference here between the primary and secondary constraints, since they both have the same structural role of being first class. That seems to be the important property here. The second argument is that this alternative picture is in tension with the equivalence class of states. So the argument here is just that on the constraint surface, this induced two form is such that it only acts on those vector fields that are tangent to the constraint surface. And what this means is just that for functions that vary along the gauge orbits, this induced two form on this constraint surface is just such that it cannot effectively see this change. And so it seems that the value of a function at different points along a gauge orbit cannot be distinguished on the constraint surface. Turn to the two questions I had at the beginning of the talk. We've now been looking at this first question: what is the correct way of characterizing the Hamiltonian formalism in the irregular case? And effectively, what I've argued is that at least in this geometric way of thinking, it seems the right way to characterize the models of the constrained Hamiltonian formalism are in terms of what I'm going to write as some final constraint surface, the surface characterized by the satisfaction of all of the first-class constraints, some induced presymplectic form, that is just the pullback of the form on the full space to this final constraint surface, and the Hamiltonian function just restricted to this surface. But now the symmetries of these models are going to include all the transformations generated by the null vectors or the null directions of this induced 2 form. That is transformations that are going to take any point to any other point along the same gauge orbit and any vector field to any other vector field that differs by just some arbitrary combination of the vector fields associated with the first-class constraints. Notice that these transformations will preserve the Hamiltonian restricted to the constraint surface. Okay, so this is at least a partial answer to this first question. So now we can turn to the second question. What is the relationship between the Hamiltonian and Lagrangian formalisms in this irregular case? So to start with, there's an immediate worry that we might have, which is just that the image of the Legendre transformation is just the primary constraint surface. And so it seems that if there's any way of relating these two pictures, the natural relationship seems to be between our Lagrangian formalism defined on tangent space and this total Hamiltonian formalism. So just to push this a little bit further, some people have argued that one can just show that the solutions to Euler-Lagrange's equations in the presence of these local symmetries, in a sense, match the solutions to Hamilton's equations under the total Hamiltonian as the thing that generates it. And this might be another way of characterizing the worry that's presented by what I called this alternative picture that I argued against earlier, which is just to say that the extended Hamiltonian formalism is not the thing that's naturally related to the Lagrangian formalism. And so if one is motivated by the equivalence between these formalisms, this might suggest that the extended Hamiltonian formalism is not the right way of thinking. And just to go back to this electromagnetism example and see why one might have this kind of intuition, well, in the Lagrangian formalism, if we consider the gauge transformations, they are just such that if we transform A, it takes us to the derivative of some function of the coordinates and time, which we just write in epsilon, and V just transforms to V plus the time derivative of that thing. So in combination, it's just like the derivative of some scalar field epsilon. But this corresponds just to a special combination of the constraints in the Hamiltonian formalism, not some arbitrary combination as would be implied by the extended Hamiltonian, precisely because we have the same epsilon here in both of these transformations. So just visually to see what's going on here, what it seems to be the case is, unlike in the regular case where we have this map from the cotangent space to the tangent space to the cotangent space and vice versa using the Legendre transformation as inverse. In this irregular case, the image of the Legendre transformation is rather some submanifold of cotangent space, this primary constraint surface. But what I argued in the first part of this talk was just that we shouldn't even think of the primary constraint surface as characterizing the constrained Hamiltonian formalism correctly. It's really this final constraint surface that is defined by the satisfaction not just of the primary constraints, but all of the first-class constraints. There are two kind of further natural questions that I think arise here. Firstly, is there a way to characterize the equivalence between the Lagrangian formalism and the Hamiltonian formalism defined just on the primary constraint surface? Now, what's interesting about this case, as I've said before, is that the Legendre transformation is not invertible, but perhaps there's a way that one can characterize the equivalence as up to the symmetries in both of these ways of describing physics. And second, is there a different way of characterizing the Lagrangian formalism such that its Legendre transformation just is this final constraint surface? And similarly, does there exist, if we can define such a version, can one give an equivalence result between this thing and the final constraint surface? Now, for the rest of the talk, for sake of time, I'm just going to focus on this first part of the second question, namely, is there even a way that we can motivate some reformulation of the Lagrangian way of doing things, such that there's a natural relationship now between that thing and this final constraint surface way of thinking? So visually, what I'm kind of asking is, just like in the Hamiltonian case, we had some way of motivating some submanifold of cotangent space defined by these constraints that we thought characterized all of the gauge symmetries going on. Is there a similar way to argue that, in a sense, the Lagrangian way of doing things doesn't capture all of the gauge freedom? Really, we can think that there's actually some submanifold of this Lagrangian space that's motivated as capturing all of the gauge freedom, and its Legendre transformation is this final constraint surface. So that is this relationship that some people have held on to between the Lagrangian and this primary constraint surface, just an artifact of the way we've set up the Lagrangian formalism in the first place. And again, just to kind of see some intuition of why we might think that we can do this, let's go back to this electromagnetism case. And this is a point that David and Oliver also make in their paper, which is just, let's consider defining some new Lagrangian, which is just the Lagrangian we had before. But now instead of V, we have V plus some arbitrariness represented by some function of the variables in time represented by mu. Now, the Legendre transformation of this Lagrangian just is the extended Hamiltonian. And moreover, it's a little subtle, but one can see that this Lagrangian doesn't differ in any physically meaningful way to the original Lagrangian. Effectively, one can show this by just thinking about what equation of motion one gets, and what one finds is that one's effectively replaced V with this V plus mu. And the thing that we measure now is not this electric field, which is the combination of the A dot and minus the gradient of V, but really it's this combination with this extra mu there. So what this suggests is just, at least in this electromagnetism case, perhaps there is a way to reformulate the Lagrangian such that actually this thing is the thing that's naturally related to the final, the extended Hamiltonian way of thinking. But the question I want to ask is, like, is there a more general way to do this so that we can see that there's a general motivation for extending the Lagrangian in this kind of way? And I think the answer to this is yes. And the way I'm going to kind of demonstrate that I think there is a way to do this is to use a geometric way of doing the Lagrangian formulation, just in the same way that I described that one could do in the Hamiltonian way of doing things. So let's turn to this geometric way of thinking about the irregular Lagrangian formalism. So first of all, we can think of the tangent bundle as being equipped with a two form. That's just the pullback of the two form on the Hamiltonian side, which can be written in coordinate form in the way that I write up here, where importantly, one term in there that's going to be important is what's the second derivative of the Lagrangian with respect to velocities, which we call the velocity Hessian. And this is important because it's just in the case where this thing is not invertible that we're in a case where we have that the Legendre transformation is degenerate. And so it's precisely in this irregular case that we find that this two form written on the Lagrangian side is in fact pre-symplectic. So we're in a state where we don't have a symplectic manifold, but we do have, in a sense, a pre-symplectic manifold. That is, we have a manifold that is degenerate, and so it's going to have null vectors associated with it. And what this means is we can write the equations of motion for some vector field x on this formalism in a similar way to we did on the Hamiltonian side, which is just, it's the two form, this two form contracted with some vector field x is equal to the exterior derivative of E, where, remember, E is this total energy function related to the Lagrangian. And one can show that when we do this in coordinate form, we just get sort of the analogous thing of the Euler-Lagrange equations. Importantly, because our two form here is pre-symplectic, this is not going to give us a unique vector field x. There are going to be vector fields, it's unique up to these null vectors of this pre-symplectic form. And moreover, the kind of thing that one can notice here is that if we have some vector field that is just one of the null vectors of this presymplectic two form, then what we find is just that the contraction of this two form with this null vector field and any other vector field x is going to be 0. So if there are points where the contraction of dE with z, that is z being one of the null vectors, is not equal to 0, then we seem to have an inconsistency with the equations of motion, since we'll have effectively the left-hand side being equal to 0 and the right-hand side not being equal to 0. So what does this mean? Well, what we can think of this inconsistency as doing as really telling us that we should really think about defining some submanifold of tangent space where the solutions of the equations of motion must lie. That is, they're just going to be the points where we do have this consistency. That is where dE contracted with the null vectors of this presymplectic two form is equal to 0. This just means is that this equation functions just as the constraints do in the Hamiltonian formalism. They give us some submanifold where we think the equations of motion ought to lie. And we can repeat this process in the same way that we did for the secondary constraints in the Hamiltonian side. That is, if we demand that any solution is tangent to this surface, we can get some further constraints. And finally, we end with some submanifold where this process effectively terminates, where our equations of motion are such that our vector field is not unique, but it will lie tangent to this submanifold. So just to say visually, the idea is that this picture is going to look very similar to the Hamiltonian case. It's going to look analogous, except for the fact that while on our cotangent bundle, we could define a symplectic two form. On this side, we can only define a presymplectic two form. But we can do the same thing when we think about the consistency of the equations of motion and define some submanifold where the equations of motion ought to lie. So going back to this other picture I had, effectively, what I've tried to answer is like the existence of this submanifold of tangent space that's motivated. But there's still left a question of whether the Lagrangian transformation of this thing is what we wanted, which is just the final constraint surface on the Hamiltonian side. And this is where things become a lot more tentative for me. So at least I conjecture that under a restricted class of these irregular Lagrangians, one can define some map from this Lagrangian constraint surface to this final Hamiltonian constraint surface that maps effectively the null vectors of the Lagrangian side to ones on the Hamiltonian side. And moreover, that any equations of motion on the Lagrangian side correspond to a solution on the Hamiltonian side, and vice versa. Now, I don't have a full proof for this. I have a reference here where it's the closest I found to someone trying to prove this conjecture. But I don't fully think, my spidey senses feel like I don't know if this is a complete proof of this thing, but I'm interested to see whether it does work. But at least I think that there are reasons to expect that this will be the case. So just to give two kind of vague gestures at why I think this is the case. The one is that the degeneracy of this two form on the Lagrangian side captures effectively the Hamiltonian primary constraints, which is just because if we think about the fallback of the primary constraints, they are null vectors of this thing on the Lagrangian side. And it captures the fact that our Legendre transformation is not a local diffeomorphism. And second, these tangency conditions, these consistency conditions that I defined, they are systematically related, at least in certain cases. The reason, first of all, is a thing I gave earlier, which is just that on the full space, the pullback of the symplectic form on the Hamiltonian side gives us the Lagrangian two form. And in a restricted class of cases, we can also say that the pullback of the Hamiltonian is just this energy function. And so if this conjecture is true, it would suggest that we can complete this picture. That is, we have motivated some submanifold on the Lagrangian side that is such that its relationship to the final constraint surface on the Hamiltonian side is just like the relationship between the tangent bundle and the primary constraint surface. So what's the upshot of this? Well, it seems that there's a sense in which the usual way of describing the Lagrangian formalism doesn't capture all of the gauge freedom that's present. And we can capture this gauge freedom by constructing a constraint algorithm in just the same way as one does in the Hamiltonian picture. And I've argued that there are reasons to expect that we can systematically relate these two analogous to the relationship between tangent space and this primary constraint surface. So just before I conclude, what are sort of some next steps of what to do here? Well, as I suggested earlier, one question would be, of course, to kind of see if we can get a kind of equivalence result here. That is, can we define some category representing the constrained Lagrangian formalism, whose objects are just the models given by this constraint surface in the Lagrangian side, and similarly for the Hamiltonian side, such that these two things are categorically equivalent. Now, as I said before, the difficulty is that just like in the case between tangent space and the primary constraint surface, we don't have an invertible Legendre transformation. So at least it's going to be a lot more subtle than the regular case. But perhaps what this suggests is we might be able to give an equivalence up to symmetry's kind of result. Second, kind of pushing the kind of argument that David Baker gave yesterday is that even if we can kind of capture some relationship, how should we interpret what's going on here? That is, should we think of this, like if we can capture an equivalent result, should we still think that there's some kind of difference between the two formalisms here? That is, should we think of them as sort of two sides of the same coin or not? And just to push that a little further, there are at least some apparent differences between the ways that we do Lagrangian and Hamiltonian mechanics. But in particular, in this irregular case, it seems that there's even more differences than just in the regular case, precisely because we don't have a local diffeomorphism. And finally, a question that I've kind of completely ignored in this talk, which is normally what people discuss when thinking about the constrained Hamiltonian formalism, is that there's a particularly interesting problem when the Hamiltonian is itself a constraint. And the reason is just that when the Hamiltonian is itself a constraint, which is normally when we think that time has some reparameterization invariant symmetries, we seem to get this issue on the Hamiltonian side that our gauged independent variables are just the things that don't change over time. This is called the problem of time in the Hamiltonian side. But what's interesting is that people at least suggest that this is a problem with the Hamiltonian way of doing things, and that it doesn't kind of arise in the same way in the Lagrangian way of doing things. So I think perhaps thinking more closely about the kind of formal relationship between the formalisms in this case as well might help to shed light on what's going on there. Is there really a sense in which this is an artifact of the Hamiltonian way of doing things? Okay, so just to conclude, just as an upshot of this, we can kind of take the alternative picture that I presented earlier to effectively have two horns. The first is to say that this extended Hamiltonian formalism is not motivated from a Hamiltonian perspective. The second is arguing that the extended Hamiltonian formalism isn't motivated from the Lagrangian perspective in as much as it's not equivalent to it. And what I've tried to do in this talk is effectively tackle both of these horns by showing, firstly, that there is a sense in which this extended Hamiltonian formalism is motivated, at least from a geometric way of thinking about the Hamiltonian formalism. And second, that there's a similar motivation for effectively extending the Lagrangian formalism in the same way. Okay, thank you, that's it.
Okay, we have about 10 minutes for questions.
So you talked about that there might be a restricted class of Lagrangian, which this kind of thing might. Do you have any kind of thoughts about what kind of restriction is appropriate here?
Yeah, so I said that this kind of result might rely on it being the case that the pullback of the Hamiltonian is this energy function, is the energy function on the Lagrangian side. Now, I think in order to have a well-defined Hamiltonian function to do that, what it would mean is that it ought to be the case that 2 points on the Lagrangian side that map to the same point on the Hamiltonian side are such that their energy function is the same. That is, it will not be the case that we have 2 points with different energy functions mapped to the same point on the Hamiltonian side. So that's at least my sense of one constraint that one might want to have, which I think probably is like physically motivated, but I'm not sure how to characterize that precisely. But I think that would kind of be important to kind of give this result.
Yeah.
So towards the end, you had a suggestion about the problem of time on the Hamiltonian side. And that this might be something that allows us to drive a wedge between the two approaches. I'm interested in hearing more about that. On the Lagrangian side, what does it look like in physical situations where we have the problem of time on that?
Mm-hmm. Yeah. The answer is I'm also interested in knowing more about that, and I don't have a clear sense of what's formally what the analogous to the Hamiltonian constraint looks like on the Lagrange side, if it even makes sense to say that there's a constraint of that kind on the Lagrangian side.
If there isn't, right, then that's a way to try between the two approaches too.
Right.
This strikes me as really a suggestive place to push.
Mm-hmm.
Very cool, thanks.
Oh, Thomas.
Can you put it back up the picture with the diagonal lines? You know which one I'm talking about?
Like this.
I'm asking on this side, but I'm wondering if, so thinking about it just like from a purely mathematical point of view, you look at the cotangent bundle in the Hamiltonian, like you can kind of tell when those guys are weird by looking at, you can do a perfectly analogous thing by looking at the fiber derivative of the Hamiltonian. And when it's not, so in the hyperregular case, that's the same as looking at the inverse of the fiber derivative of the Lagrangian. Or the fiber derivative of the energy function associated with the Lagrangian, or whatever. So I'm wondering if that gives you a way to build down below, doing the same thing.
That way, the other way around. I see.
It's a bad question, but
No,
I'm sure it's clear in my mind.
Yeah, so the question is, we can, at least in the regular case, we don't just have a Lagrange transformation. We can define the same kind of thing from the Hamiltonian.
Yeah.
Cotangent bundle to the tangent one. So in the irregular case, what does that map look like?
Yeah,
Does it also come down?
Come down.
yeah.
Yeah. I don't know. I actually haven't asked that question.
And if it does, can you use that to build these other iterations below on this side?
Which would be something like, what would that map look like when now restricted to the primary constraint?
And what does that map look like when restricted to the final constraint surface? I mean, does that, because I don't think you're claiming that FL prime is invertible. And so we've got some other map, and does it keep going down, or is it, I mean, I guess it can't go back up. Yeah, that's interesting. Do you have another question?
Yeah, I'm just thinking about these this kind of hierarchy of constraints in the Lagrangian case. So at least in the physical significant examples that I'm aware of, then one way to think about the Hamiltonian Lagrangian relation is that the primary constraints are occurring because the Legendre transform is one-to-one. But then the secondary Hamiltonian constraints are occurring because there are constraints on the Lagrangian side. You see picked up in the framework, given difference in electromagnetism. The primary constraint isn't telling you anything about physical constraints on the Lagrangian side, but div equals 0 absolutely is. That's a Lagrangian constraint.
Yeah.
Now, in all the cases I'm familiar with from sort of field theory type context, then there tend to be conservation laws on the Lagrangian side that mean that there's no further problem in, if you impose the Lagrangians, effectively you solve the Lagrange equations at one time, then they're going to continue to solve later. And that tends to be related to some kind of symmetry and to theorem type effects. I'm just interested if there are good physical examples of cases where the Lagrangian side constraints don't close in that friendly way, where you do genuinely need these additional constraints. I imagine there are, but I just don't have a very good sense of these things outside field theory.
I don't have a good example, but I think finding a nice simple example would be a very useful thing to do to understand if there, like, we obviously don't do Lagrangian mechanics on this submanifold thing that I described. So is there a sense in which there's a way in which we think we ought to do it on that?
Well, we sort of do and we don't we? I mean, again, in electromagnetism or GR or any of the sort of parameterized gauge theory type stories, we do in the sense that some of the early Lagrange equations are straight equations. And so it is the case that the div, in vacuum electromagnetism, the divi not equal to zero points in the tangent space. Well, you could debate how to think about them physically, but in any case, they don't correspond to dynamically possible states of affairs. Arguably, they don't correspond to kinetically possible states of affairs. But we don't, in that situation, there are no further implicit constraints because the gauge freedom gives you a inertia result that says that the conserved quantity, the constraint is conserved quantity, div equals zero div is conserved if the other things hold. So if you impose div equals zero at the initial time, it continues being imposed. So we do have it, but we have it in quite a friendly way. I'm interested by and can't think of any examples of, but it seems like there should be examples of cases that aren't as friendly as that, where there is a real constraint, but the constraint's not automatically conserved, so you get further implicit constraints.
Right. Thanks. Yeah, I would need to think about that.
Sure.
I think that there are examples to look at in some of the examples that Clara looks at in partial differential equations of physics, where you have problems of your constraints not being complete, how he deals with them. I mean, he's not, in most of the papers, not talking about Lagrangian mechanics or Lagrangian field theory, but it does have the same kind of character. And I mean, I don't think it's an accident that the word constraint is getting used all over the place here, because in fact, the Maxwell constraints are the Maxwell constraints, right? And you get them from extremizing the action, but you can also sort of see them from consistency conditions on initial data for there to even exist a initial value problem. And so I would guess that if you tried to write down a Lagrangian theory for a system of equations, like a Lagrangian for a system of equations, whose constraints were not complete, that you would then need to augment with additional constraints, that you would end up finding that there was a problem with the Lagrangian formulation that would push you to do something like this. Join me in thanking Clara.
So we will take a 10-minute break for coffee, and then resume with our final speaker.
That would be great.